Hello, my name is Aiden Benton, and I'm going to be doing a redux of my Capstone presentation, as unfortunately the video of the original presentation has been lost. And as you can see from the date, it has been a little while since I have given this presentation, so please bear with me. I gave it in April, and it's now September. So I am going to do my very best to match what I did, but there are no guarantees it'll be exactly the same. So without further ado, Modeled Modules is a project to create SuperCollider extensions based on real-world synthesizer modules. So first, I will be discussing the history of computers, synthesizers, and computer music to provide context for the project. Then I will be discussing the project itself, including the modules I've implemented and the process of implementing them. Alright, let's get started. The history of computer music is a long and storied one, beginning with the earliest analog synthesizers and continuing to the present day with the advent of digital audio workstations and software synthesizers. And I think from analog to digital and back again is quite a clever description, as we started out with analog synthesizers, we went to the digital, and now everyone wants to use analog synthesizers again because they're great. What is an analog synthesizer? An analog synthesizer uses electricity as an analog to sound waves, creating a continuous signal that can be manipulated in real time. Since sound waves are just vibrations in the air, an analog synthesizer can create any sound that can be produced by a physical object vibrating at a certain frequency due to the electricity's ability to mimic these vibrations through voltage. Kind of technical, essentially. A synthesizer, it's almost like a microphone without the sound input. So sound goes in, turns into electricity, sound comes out, except you just make the electricity and sound comes out. One of the earliest synthesizers was the teleharmonium, invented by Thaddeus Cahill in 1896. The teleharmonium used rotating discs to generate sound waves, which were then amplified and transmitted over telephone lines to subscribers who could then listen to the music over their telephones. It was even polyphonic. It was also absolutely massive and drained huge amounts of electricity. It was like over 600 tons of metal. The numerous drawbacks and the dawn of the First World War led to it being dismantled for parts. The theremin, invented by Leon Theremin in 1920, was the first electronic instrument to be mass-produced and sold to the public. It used two antennas to control pitch and volume and generated sound using a technique called heterodyning, and was famously used in the soundtrack to the 1951 science fiction film The Day the Earth Stood Still, due to its otherworldly sound. I recommend checking out more about Leon. His life was kind of crazy, and he invented a bunch of cool stuff. The onde Martineau was similar to the theremin, but used a ribbon controller instead of antennas to control pitch. And the orgue des ondes was arguably the first programmable analog synthesizer, using 700 vacuum tubes to generate sound waves rather than heterodyning, giving it 10 different timbres for its 70 keys. It used an early form of additive and subtractive synthesis, but the complexity of the instrument and the new portable Hammond organ led to its demise. And here we have a picture of some guys working on some of these vacuum tubes of the orgue des ondes, and a picture of one of the variations of the onde Martineau. Moving on, following the orgue des ondes, the Trautonium was invented by Dr. Friedrich Trautwein in 1930. It too used a vacuum tube oscillator. Although being a single tube, it was passed through resonant filters to create different timbres. Oscar Sala was a virtuoso of the Trautonium and used it in a number of film scores, including Alfred Hitchcock's The Birds. He continued playing and modifying the machine up until his death. The Volkstrautonium pictured here was a simplified version of the Trautonium created by Telefunken that was marketed to the public. It was so expensive that very few were made, and they are rather rare nowadays. Here is a picture of Trautwein on the left, Hindemith in the middle there, and Sala playing the Trautonium. Hindemith actually did compose a piece with the Trautonium in it. Fascinating. The first machine to call itself a synthesizer, however, was the RCA Synthesizer 1, created by Harry Olson and Herbert Billar in 1951. The development of the machine was originally funded by RCA to create a machine that could replace studio musicians and even completely replace musicians by generating hits. No more musicians at all. AI can't even do that today. So they were really, really ambitious. They did end up creating a fantastic machine, but it wouldn't do what RCA first intended. The machine was monophonic and used a series of oscillators, filters, and amplifiers to generate sound. The machine was also so complex that it had millions of settings, all programmed in a form of binary on a roll of hole-punched paper. The machine was used by a number of composers, including Milton Babbitt, who used it to create his famous piece, Composition for Synthesizer. It unfortunately now sits in ruins in a basement somewhere, which is sad. Here is a picture of the Mark II schematic, and if you're familiar with modular synthesizers, you may notice names you recognize, but keep in mind, this took up like a whole room. And nowadays, these things could fit in the palm of your hand, which is absolutely crazy. So, synthesizers would begin to enter the popular sphere in 1964 when Bob Moog created the first prototype of a modular synthesizer called the Abominatron for his friend Herb Deutsch. The idea was to create a machine that could generate any sound imaginable, and the modular synthesizer allowed for such a large number of combinations that this goal was pretty much realized. The first series of synthesizers was just titled the Synthesizer series, which started with the Moog Synthesizer 1, which was released in 1964 and offered the basic needs of a synthesizer in a portable package. Well, then we moved to the Synthesizer 2, which was released in 1965 and was designed for more complex applications in studios and universities. This version is the portable version, but I'm not sure how portable carrying around a 200-pound synthesizer is. Oh, and the keyboard. You also need the keyboard. And of course, the Moog Synthesizer 3 was the first fully realized synthesizer and was released in 1967. This is also considered the portable version and comes in the size of now even less portable with its 3 cabinets there. And now we get to the most iconic synthesizer of all time, the Minimoog Model D, which was released in 1970. It featured hardwired common synthesizer routings to make it easier for beginners to use, and it came included with the keyboard. It was integrated into there, and it was also the first to ever be sold by instrument dealers and was widely adopted by musicians, including artists like Stevie Wonder, Kraftwerk, and Gary Newman, and it really became the archetype for all synthesizers that came after. Then in 1977, Dave Smith and John Bowen released the Prophet 5. The two had been working on microprocessors and thought it was odd other synthesizer manufacturers hadn't implemented them, so they made one themselves. The Prophet 5 was the first synthesizer to combine analog and digital technology, allowing for the best of both worlds. It used analog components to generate its sounds, but used digital memory for storing custom presets and allowing for sensitive keyboard scanning. It was the best-sounding and most popular polyphonic analog synthesizer of its time due to the ease of use that the additional digital components added to it. The 80s then saw the rise of digital synthesizers and samplers, which replaced their purely analog counterparts like the Roland TR-808 drum machine and the TB-303 bass synthesizer. However, as digital synthesizers became expensive, the analog synthesizer market began to grow again. And now a genuine TR-808 can go for thousands of dollars. The unique sound of analog synthesizers is likely never going away because it just sounds so different than what digital can try to replicate. And now, developing along synthesizers were general-purpose computers, starting with Electromechanical computers. The first digital computers were electromechanical, meaning they used mechanical switches and relays to perform calculations. And the first electromechanical computer was the Z2, which was invented by Konrad Zuse in 1939. The Z2 was the first modern computer to use binary arithmetic, which is the basis of all modern computing. It was unfortunately destroyed in World War I. Another example is the bomb, which was invented by Alan Turing in 1941. The bomb was an electromechanical code-breaking machine that was used to decrypt the Enigma cipher during World War II. Then, the introduction of vacuum tubes allowed for relatively much faster computers due to everything being processed electrically without the need for mechanical parts. One example is the ENIAC. It used panel-to-panel wiring and switching to program the machine. It was used to calculate artillery firing tables for the US Army during World War II. Another example is the Manchester Baby, which was the first computer that ever ran a digital electronic stored program. This was different to how previous computers worked because instead of being designed to execute one function, like calculating artillery tables, the computer could execute an arbitrary program stored in its memory. And we also get, around this time, the first application of a computer for commercial purposes with the J. Lyons and Company with their Leo 1, which was used to manage bakery operations like scheduling production and delivery of cakes. Then the invention of the transistor happens, and it is quite the revolution. They were smaller, required less power to operate, gave off less heat, and were more reliable than vacuum tubes. The Manchester TC was the first computer prototype to utilize the transistor. It was also during this time that IBM entered the computer market with its IBM 701 mainframe, known as the defense calculator. It was the first ever computer to play checkers, fun fact. The IBM 704 was considered a large upgrade from the 701 and was designed to solve complex problems in large-scale settings, and was considered a supercomputer at the time. And here we'll find a picture of the IBM 704 mainframe taking up a whole room and looking rather big and complex, and it was, but it was powerful. And now we get to a very critical moment. In 1955, Max Matthews was hired at Bell Labs and began working with their IBM 704, and he was the first person to create music on a computer and create the first program to even create sound on a computer. The series of programs created by Matthews was titled Music N, with the first program being Music 1 in 1957. It was, to quote Matthews himself, terrible. It could only generate a single triangle wave with the possibility to change the pitch, loudness, and duration. The first piece of music created using Music 1 was in the silver scale, and it played over the speakers in Bell Labs and was 17 seconds long. The second iteration, Music 2, was created in 1958 and added 4 voices and arbitrary waveforms. This was achieved using a new concept called the wavetable oscillator. Rather than generate waves from scratch, the wavetable oscillator would store a number of pre-generated waveforms in a wavetable that could be accessed and manipulated. So rather than having to create new waveforms every time you wanted a custom waveform, you could just take one that existed and manipulate it using mathematical operations to get it to where you wanted it to be, which is much less resource intensive. Music 3 would introduce the important concept of the unit generator, or UGens. These are the building blocks of generating audio signals and support a number of different control inputs to change parameters. Then also introduced was the idea of instruments and orchestras. An instrument is a bunch of UGens collected together to create one output, and an orchestra is a collection of those instruments. Pretty straightforward, but for new computer musicians at the time, it probably made a little bit less sense. Now, with Music 4, a copy was given to John Chowning. the later inventor of FM synthesis, by the way. He was able to hook up a computer running Music 4 to a computer running a digital audio converter to create the first integrated music system. And at this time, things were running, we don't have real-time sound synthesis yet. We also get Music 5, which here we see was written in Fortran. Fortran was the first programming language, and that means it could be used to write programs for multiple different platforms. Prior to this, code had to be written for each individual computer, as they would interpret instructions differently. Keep in mind, again, this is all being done on punch cards and mainframe computers. In fact, the stack of cards we see Matthews holding in this picture here is only a part of the full Music 5 program. Then, with the advent of microprocessors, workstations, terminals, and operating systems, music programming advanced in accessibility, and so did computing as a whole, especially with the invention of the Unix operating system and the C language. In fact, Gareth Loy and Richard Moore invented the Carl system, which was in fact based on Unix and written in C, which took the idea of interconnected programs for text processing used in Unix and did that for music, making it rather modular. It was also open source and extensible through its API, leading to the creation of C Music, an implementation of Music 5 in C created by Richard Moore for the Carl system. And again, we don't have live real-time audio creation, so here's an example of what we could do. We could specify we want a waveform, a wave that is a sine with the frequency of 440 hertz, and by using this vertical line, we call it a pipe. We send the output of this to our spectrogram, and that's how you would do it. There were many more programs at this time written in C, created for computer music. CMix was created by Paul Lansky and was a C language library and scoring language. It also had support for Mink, which stands for Mink is not C, which allowed for C code to be written in the score files themselves. This added the ability to create algorithmic compositions with things like loops and variables and all that fun stuff. CLM, or Common Lisp music, was created by Bill Shostat in 1985. A modern Lisp music language is Nyquist, which is used by the Audacity editor. And finally, C-Sound was created by Very Vercoe in 1985 and was the most popular descent of Music N. It was written in C and could be used for real-time audio synthesis. Crazy, we got there. It also introduced the concept of running UGens at audio rates and control rates, abbreviated as AR and KR. This allowed users to save on computer resources when they weren't using the UGen as an audio signal. CLM and Nyquist use Lisp, and here's an example of some CLM code. You may notice the rather unintuitive, in my opinion, use of 1 billion parentheses, but that's just Lisp for ya. As we get more real-time audio, we also get graphical interfaces, we get graphical interfaces, and we also get the creation of the program Max, created by Miller S. Puckett at ERCAM. It was originally used as a way to send control messages to sound devices, which would then generate the sounds. And then in the 1990s, ERCAM licensed Max for commercial use. So Puckett went on to take his original ideas and create Pure Data, which is the open source version and is free to use. And it also added the ability to perform its own signal processing, able to make sound on your computer. Max was then extended to include those signal processing capabilities, and Max MSP was born. The MSP is said to stand for either Miller S. Puckett or Max Signal Processing. And here is what the Max MSP interface looks like. It uses a visual interface to allow for manipulation of sounds and waveforms and all that jazz. Then we get to SuperCollider. In 1996, Jay McCartney invented SuperCollider, which is the most important part of this project. The language is again implemented in C. Like many other computer music applications, as we've seen. Haha. SuperCollider is made up of 3 components that all work together. The first is SC Synth. This is the actual real-time audio server that executes SuperCollider code and generates that real-time audio. And it can be communicated with via the OSC standard and can also be used by any program or application that knows how to communicate with it. The second component is SC Lang, which is the interpreted programming language for writing SuperCollider code. And finally, we get SC IDE. IDE stands for Integrated Development Environment, which is essentially a fancy way of saying this has all the tools for you to write code for this thing. So this has all the tools for you to write code for SuperCollider. So it includes an easy way to manage the server, easy way to make sure the interpreter for the language is running, and my favorite part, has an inbuilt documentation browser, so you can easily look up basically anything and read about it in the same text editor without having to leave, and that really speeds up programming sometimes. But again, why? Even with all this history, why work with SuperCollider today? Why care about analog synthesizers? To answer that, I have a few examples of musicians who changed the way we think about music. Starting with Wendy Carlos. Wendy Carlos brought the Moog synthesizer into the mainstream with her album Switched on Bach in 1968. The album was the second classical music album ever to go platinum and won 3 Grammy Awards. It required thousands of hours to put together due to the monophonic nature of the synthesizers and the polyphonic nature of the material. Carlos would go on to compose music for a number of influential films, including A Clockwork Orange, The Shining, and Tron. Her work has inspired a number of modern composers, including the composers of the Stranger Things soundtrack. Next, we have Kraftwerk, which was founded in 1970 by Florian Schneider and Ralph Hütter. They are, in fact, considered the Beatles of electronic music, and have been highly influential in a number of electronic and popular music genres. Their album, Autobahn, was released in 1974, and the single edit of the title track became an international hit in 1975. I think Schneider captured the evolution of electronic music when he noted, quote, "We are more like vehicles, a part of our Mensch machine, our man machine. Sometimes we play the music, sometimes the music plays us, sometimes it plays." And now for a more modern example, we have the EDM artist deadmau5. Pictured here is his studio, which contains walls of physical synthesizers. He is also a fan of a program called VCVRack, which provides digital implementations of analog modules and provides an interface that reflects working with physical modules. When it comes to the digital versions of modules, he believes, quote, "A lot of those oscillators are great. Obviously, not so much the analog oscillators like you get out of a Synthia or something like that, but the digital oscillators, all the wavetable stuff, and the digital FM ops and stuff like that are fucking great." He has said that his current 2 favorite synthesizers are the Analog Solutions Colossus and the Moog Voyager. But at the end of the day, with all this context, why choose SuperCollider to be the implementation of this project? Well, SuperCollider makes the kind of extensions I wanted to create easy through its API for SC Synth. It's extensible and has good documentation on how it's extensible. Despite the main codebase being written in C, modern extensions use the C++ adapter for the API. And I was already familiar with C++, so that made things a little bit easier. I also had the opportunity to go beyond just copying the modules one-to-one. I could remove some of the limitations that being an analog physical module had in favor of adding that extensive customizability that digital can offer. So the first module I worked on was the Boolean logic module, and this was a great one to start with due to the fact that Boolean logic is very digital and very simple to implement in almost any programming language. So it was based on the Wavephonics Boolean logic module, and the module only offers 4 types of logic gates: AND, OR, NAND, and NOR. Implementing logic into this kind of analog circuit is probably more difficult than it is in code, And I was also able to add an arbitrary number of operations, as we can see here. This is my, excuse me. This is the C++ code for the extension. You'll notice a lot of this kind of crazy fancy looking code. That is just boilerplate for the API, where everything really happens in these extensions, these unit generators, in their next function. This is essentially the function that's called every time the system wants another unit generated from the UGen. So here it's rather simple. We have two inputs that we take input 1, input 2, and depending on the selected operation, we choose that operation to perform on the inputs, take the absolute value because the waves could possibly be bipolar, meaning they can have negative values, but a negative value is still going to count as a signal compared to 0. So we take the absolute value of that to check if it is any value greater than 0, and then we compare those using the operations like an and depending on that, we output literally a 1 or a 0. When I said it was pretty simple to implement in code, this is what I meant. This is what code is really good at doing. So when you do make an extension, you also have to write the SuperCollider object for that extension. So here is that implementation. The one interesting thing about this is the use of these aliases, which allow you to put in the name of the operation rather than just the corresponding number to make things a little bit easier. And this only runs at a control rate value. Now I will play an example in SuperCollider for you.
SuperCollider. 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 SuperCollider.
So for the next module, there was something really, really important that I didn't know going in, but I definitely learned while I was trying to do the module. DSP is hard. DSP stands for Digital Signal Processing. And this is essentially the mathematics, engineering, and theory behind turning sound into a digital signal. Because if you didn't know, sound is made up of a wave that has infinitely many precise values, and a digital system can only represent up to a certain level of precision. So you have to figure out where you're going to best replicate that with that loss of precision. We're really good at it now, pretty good at it now, but the actual theory is pretty difficult. And the module I learned this on was the ripples module. The ripples module was actually based upon the mutable instruments ripples module, which has filters. And if you are familiar with DSP, you know that filters are not very simple. I thought they would be pretty simple. That's why I chose to do this one second, but they weren't. So this model uses resonant filters. However, my version uses Chebyshev filters, which have a parameter called the ripple in them, which I thought was kind of fun. But other than that, it was kind of an arbitrary pick of what kind of filter I wanted to use. It doesn't have things like a VCA or anything that's required for like an actual physical module. And when I was making this, I tried to create and understand how to create my own filter implementation. And I tried at it for a long time. It took all I could make though was a filter that just generated random noise. To this day, I don't think I completely understand how those filters work, although I'd really like to kind of look into that. It just was beyond the scope of the project. So what I did do, as we look into this C++ implementation, is I used an external library that implemented these filters. So what that essentially means is I used someone else's code, but in a way that's allowed because they published it. So the implementation ends up looking rather simple. because the majority of the code is implemented in the library. So we just take the input, and then we have 3 separate outputs for each of the separate filters. Of course, we need to calculate the width of our bandpass filter by using the reciprocal Q times the center frequency. And then you just set up the filters, zap the gremlins, and output it. Zapping gremlins is removing any weird values like not a numbers and infinities. This is actually a function that's included in the API, which I thought was very silly and also fun. So in C++, you have something called a header file and the actual C++ file. The header file is basically where you go, this is what I'm going to implement, and the C++ is that implementation. So here in this header file, you'll see that I include the necessary plugin library and also my external library, IIR, which stands for Infinite Impulse Response. That's just the kind of filter that I used. And so you'll see here, I set up variables that are going to be these filters that I then set up in the C++ implementation. So for me, I don't have a lot of code to do, but if you went and looked into the library, which you can, it's an open source library on GitHub, you could see the very complex nature of filters there. And now for the SuperCollider object, we do have an audio rate and a control rate. The one thing I'm proud of is this specific method here, which allows which creates output proxies. Essentially what this does is it allows you to operate and use the different filter outputs separately or mix them all together. So this gives you some fun options on whether you want to, put a delay on just one of them or this or that. But yeah, that's what that does. All right, and now I'm going to show you an example of how that sounds in SuperCollider.
SuperCollider, 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 SuperCollider.
Okay, and now the last module I implemented was the DIY delay module. I held off on this one because I did know that delay requires memory. And memory allocation is notoriously finicky in computer science because if you do it wrong, your computer has a really bad time. The DIY delay module is based off of the EricaSynths DIY delay module, which includes digital and tape delay, the ability to overlap, hold, and reverse with controllable feedback. So I added the option to include tape saturation, hold, and reverse. It also has this add function, which kind of serves as like a looper. The implementation of that was kind of outside the scope of this project. So let's get into the dreaded memory. So this is actually the most code heavy and complicated of the implementations. So I'm going to do my best to explain things in a good manner that is both concise and understandable. Some of this stuff gets into like mathematics behind how it works. I don't even fully understand some of the things, but I'm going to do my best. So we're going to get into the implementation here, starting simply with the constructor. So this is the method that sets up the thing that's going to call next on. So it's basically what we need every time we want to make a new one. It constructs it. So we need a maximum delay time. This is absolutely necessary because that tells us how much memory we have to allocate. What is going to be the maximum amount of memory we need to allocate based off that delay. We create a buffer size, which we do by multiplying the sample rate by that delay time. So we'll get the number of samples that will be the maximum delay. And we use this built-in function called next power of 2, specifically so we can do some programming skullduggery and use a bitwise operation rather than use a modulus operation, which isn't super important for non-technical folks to understand. That's why this is here, and that's also why the mask is the length of this buffer minus 1. And then here is the loathed memory allocation. This is not this default vanilla C or C++ way of allocating memory. SuperCollider comes with its own special memory allocation function, which saved me from having to deal with the memory stuff because the SuperCollider guys just did it themselves. So I was kind of scared for nothing. So then we create this buffer that is the memory allocation of the size of delay we need. And of course, if it fails, then we just throw an error and say, uh-oh, you couldn't use that much memory. Because if you try to continue without it working, it'll cause all sorts of problems, and that's no fun. And then the last thing we do is we fill that memory buffer with zeros. So we just zero it out. Moving on to the next function, this is where the meat of the code is. So first thing we do, we get our inputs, right? And then we get to the fun part of using these local stateless variables, as it said. For my non-technical folks, it basically allows us to create temporary holding things for our main holding things that we don't want to change. So we have, one thing I want to point out is we have a write and a read, because if we're going to do reverse delay, we are going to be reading and writing in opposite directions because we're going to be reversing. Here, this is for some safety. If they input a delay that's greater than their max delay, we just set the delay to the max delay because otherwise it would not work. You can't delay more than you asked to in the initial part. So this is this here is some delay DSP magic. I say magic, math. I am not 100% sure exactly how it works. I have to be honest. But what it is doing is we're getting the fractional portion of the delay. So we take the sample rate times the delay. So how many samples are we delaying? And then we turn that into an integer. So we remove any decimals, remove all decimal portions of it. And then we take the number of samples and we subtract that integer, and that leaves us with just the fractional value. What that is used for later is this cubic interpolation method here. Again, this comes built into SuperCollider. I can't really tell you what it does. It is a way to make sure the delayed samples don't sound crackly or aren't crazy. The mathematics is kind of beyond the scope of this project and beyond my current knowledge. So here is kind of the main thing is while we're operating on our samples, we go, okay, so read the sample. We got the first sample we're going to read. What number is that? What's the one before it? What's the two before it? And what's the one after it? Okay, so these are the samples we're going to be outputting that are the delayed samples. And this is that bitwise operator I was talking about. Essentially, it makes it so if we have like a list of 30 samples and the number is 31, we're trying to get the 31 item, it'll go up, that doesn't exist, and go back to 0, the start. And here's that cubic interpolation, which turns into our delayed sample. And then you set the out sample, zap those gremlins. You take the feedback, which is just the volume of the delay, multiply that by the delay, and add it to the original input signal. Of course, then we add our options. We have, if it's tape delay, we apply the saturation to it. And if we have the hold active, then instead of writing out to the memory buffer, we just keep the same one going over and over and over again, rather than updating it as the sample plays. Then we increment the write, increment the read, and go back to the beginning. And of course, we set the memory so the next time it's called, it'll start at those locations. Now, let's go over to SuperCollider and hear an example.
SuperCollider, 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 SuperCollider.
I'd like to thank you for taking the time to watch and listen to this presentation, which again was the presentation for my senior capstone project, which took place in April of 2024. I did my best to approximate what I did there here. And speaking of the bibliography, if you'd like to look at the bibliography, there is a link to it in the description of this video. Again, thank you for watching and listening. I've been Aiden Benton, signing off.